In this video, we're going to be looking at several laws governing gases that were discovered over the course of, as I mentioned in the previous video, several hundred years, but that underlie all of the understanding that we have about gases. And we've then taken these laws and combined them into what we know as the ideal gas law, which you might already be familiar with if you have taken a chemistry or physics class in high school. But let's go through these gas laws, and we can use these gas laws to make predictions about what will happen with gases as we change things. So the first gas law is known as Boyle's law. They're all named after the first discoverers of these laws, as we tend to do in science. I believe it's Charles Boyle. I can never remember. Robert Boyle. I can never remember their names. But Boyle's law relates pressure and volume. Right, pressure we discussed in the previous video, volume just being, how much space does the gas take up. And specifically in the cases where we have a fixed amount of gas, meaning number of moles. At the time, they didn't know about molecules and moles, but Charles Boyle was still able to figure out this relationship despite, not knowing this, and also for a fixed temperature. So this is if you are able to control those two variables. So controlling the amount of gas is pretty straightforward. You have a balloon or something, right? And you don't let any in or out. And then you have it in a fixed temperature. If you increase the pressure, so if P increases, the volume of a gas will decrease. So these are inversely related. And same thing if P decreases, then volume will increase. And so we can write this down mathematically in this way. These are inversely related. So what you say is that the pressure, this symbol here means proportional to, meaning there's a constant involved, but we don't know what it is. So it's some constant times 1 over volume. So meaning exactly what we said above. Mathematically speaking, that's if P increases, V decreases. If V increases, P decreases, right? These are inversely related. Another way of writing this is that if we take P times V, that'll be equal to some constant, provided that our number of moles and our temperature are fixed. All right, so that's specifically Charles Boyle's law. One consequence of this is that if N and T are constant, need to add that, are constant. That means if we if we have two different sets of conditions, say we have P1 and V1, at some other, provided that the number of moles of gas and the temperature stayed constant, the product of that same gas under two different pressure volume conditions will be the same, right? Because they're equal to a constant, and that constant depends on N and T. And as long as N and T are constant, then this is constant. So we can use this to determine quantitative relationships between pressure and volume for gases. Okay, so that's Boyle's law. Next is Charles's law. Charles's first name is Jacques. He's a French scientist. All right, and so Charles's law relates volume and temperature. And similar to Boyle's law, we're going to hold other things constant. So if the pressure is constant and the number of moles of gas, then what Charles measured was that if you increase the temperature, you increase the volume. So if T increases, V increases. So they go up together. They go up and down together. Or if T decreases, V decreases. So if you take a volume of gas and you cool it down, it's going that volume will shrink, provided the pressure stays constant. So if you do it in, say, an atmospheric pressure. One really dramatic example of this is if you take a balloon and you put it in liquid nitrogen, it will shrink down completely tiny, which is a really fun experiment to do. So you may or may not have ever seen that, but that's a really fun one. Okay, so again, another way to write this is we can rearrange this equation to say, instead of V is proportional to T, V over T is equal to a constant. So just, multiply by 1 over T on both sides here. that leaves some constant behind. That's your proportionality constant. And similar to before, we can write an equation that looks like this. If we consider two different conditions, say we start with one volume and temperature and we move to a different temperature, we can predict the volume, provided, again, that P and N are constant. So that's always the key here, is that you have to have the things that are constant need to stay constant for this to apply. Okay. One interesting thing with Charles's law is that this was the first way that scientists could measure absolute zero, because you can extrapolate what volume or what temperature you would expect to get zero, a volume equal to zero. Let me find the plot here. Here it is. So this is a figure from your textbook showing what this looks like. Again, let me just make this a little bit bigger. So this is for 3 different quantities of gas. So we have different numbers of moles plotted against temperature. We have both degrees Celsius, 3 Kelvin. Now, one thing I forgot to mention is that the T's involved here need to be in Kelvin. It needs to be an absolute temperature scale for this to work. So this does not work with degrees Celsius. So what we can see is that if you extrapolate all of these data points, they're all following a straight line. That's this relationship between V and T. There's a proportionality between them. But what happens is eventually the gas will condense and form a liquid. But in theory, you could, if there was something that didn't turn into a liquid, helium is actually a really good example of this. It's really hard to make liquid helium. If you keep going and going down in temperature, there will be a theoretical point, and for all gases it's the same point, where the volume would extrapolate down to 0, and that is the point that we call absolute zero. So that's the lowest possible temperature we can get, and we get this if you have 0 Kelvin, that's equal to negative 273.15 degrees Celsius. Okay, so that's another interesting tidbit that comes from this law. All right, let's keep on moving on. We have a couple more laws, and then we will look at the combination of these, what we call the ideal gas law. All right, so the next one is Avogadro's law. So just same Avogadro of Avogadro's number, Amedeo Avogadro. And this is related to moles. So Avogadro, this is part of how he figured out the idea of that we have a bunch of molecules that are present. Right, and so this is now, we no longer have the number of moles that are fixed. Instead, we're fixing the pressure and temperature. So if P and T are constant, what can be observed is that our volume is going to be proportional to the number of moles. So essentially, the more gas that you have, the greater space it will take up. This makes sense intuitively once you understand what's actually happening in terms of there are more atoms in there, right? And so if you have something that can stretch, this is essentially, if you blow into a balloon, it'll take up more volume, provided the pressure is constant, right? Pressure and temperature are constant. So you can think of this as the balloon blowing up equation, if you want. And similar to the previous ones, we can write this as V over N is equal to some constant. All right. Again, we can use these specifically to do some calculations, and we'll do some practice with that. Both do an example calculation here, and we'll do examples in class. All right, and then I just want to finish this off. We have one more law, and then we'll be done with this video, which is Amonton's law. And this is one that I was not familiar with the name of this law, so this was actually new to me. I probably learned it at some point. But this one is thinking about keeping V and N constant. So if we have a fixed volume container with a fixed amount of gas, the pressure is directly proportional to the temperature. So again, if you increase the temperature, then the pressure will also go up. So these go up and down together, pressure and temperature. And so if you have some fixed volume container, say something made out of glass or metal, if you heat it up, the pressure, you can measure the pressure, and the pressure will increase in it. All right, and so that sums up what I can present in one video took, again, like I said, hundreds of years. So Avogadro lived in the 17 to 1800s. Amonton lived in the 16 to 1700s. Let me get my years here. Jacques Charles lived 17 to 1800s. And then, like I said, Boyle was all the way back in the 1600s. So all these laws were developed over the course of many decades of research. But now we generally combine these all into one single law that combines all of these measurements and all of these proportionalities that were observed with gases experimentally into a single equation, which we know is the ideal gas law, which we'll look at in the next video.